Analytical Chemistry 1, Lesson 43. By choosing the right counterion, we can induce a dissolved species to abruptly precipitate out of solution. What would happen if there were two or more precipitable species in a solution at the same time? First, let's look a little closer at what is happening when we start to add a precipitating ion to a solution. Here's 100 milliliters of a 0.1 molar solution of iron 2+ ions. We can form it with ferrous chloride as it is very soluble. And we will add sodium carbonate, and we'll choose it to also be 0.1 molar. The carbonate will react to form iron carbonate, which is sparingly soluble and has a KSP value of 2.1 times 10 to the minus 11. Now this is a graph where we will follow the concentration of carbonate in the solution as we increasingly add it. We will plot the concentration as a p function, just like pH or pOH. It's the negative base 10 log of the carbonate concentration. And just like with pH, when the number is large and positive, that is when the concentration is the lowest. At the start, unlike with the aqueous solutions we encountered when doing the acid-base work earlier, the amount of carbonate at the beginning is 0. So the graph starts up at positive infinity. The solubility equilibrium expression will determine the concentration of carbonate at which the iron will start to precipitate. When it increases from 0 to the nevertheless very small value of 2.1 times 10 to the minus 10 molar, which is a p carbonate value of 9.678, then iron carbonate precipitation will commence. So it starts at this level here. So when we add the tiniest portion of the tiniest drop of carbonate, the carbonate's concentration leaps from positive infinity down to the p carbonate value of 9.678. Why does it not continue to drop as we add more? Because from this point on, virtually all of the carbonate we add goes into forming the precipitate rather than staying in solution and increasing the carbonate concentration. As we continue to add carbonate, the precipitation of iron carbonate continues. The residual solution concentration of carbonate does slowly increase. Now this is because it doesn't quite all go into precipitate, because as we remove iron from the solution, its concentration is decreasing, and therefore the carbonate that's necessary to continue precipitation, it slowly increases as well. But as we approach the condition where we've removed the iron from solution, the carbonate concentration starts to rapidly increase again. The vast majority of the iron has now been removed from solution by precipitation, and now we are starting to accumulate excess carbonate. Now tiny amounts of iron remain, 10 orders of magnitude less than what we started with. But the rate of increase in carbonate concentration begins to slow down and level off as the solution concentration starts to approach the concentration of the added carbonate solution. And yes, this looks just like the titration of a base with a strong acid. And when we reach this point, which we could call the equivalence point, since the amount of added carbonate is exactly equivalent to the amount of original iron, now don't forget to include stoichiometry. In this particular case, it is 1-to-1, so the volume of carbonate is the same as the volume as that of the original iron. But in other cases, the stoichiometry may give rise to a ratio, but they are stoichiometrically related. So at this point, before we've added any carbonate in excess of the stoichiometric amount, the solution is like a solution to which the solid iron carbonate has been added. The concentrations of the two ions are the same. The amount that is not precipitated out is just the same as the amount that would have sparingly dissolved if solid iron carbonate had been added to pure water. In this case, the concentration is just the square root of KSP, or 4.6 micromolar, which is at p carbonate equal to 5.339. So at this point, the iron concentration has dropped from a starting value of 0.1 molar down to this value of 4.6 micromolar. The iron carbonate is present as fine white powder dispersed throughout the solution. If we wanted to successfully filter it, collect it, and weigh it, we would have to do some things to increase the crystal size and the purity, but for now, let's just recognize that we have removed 99.9954% of all of the iron that was originally present in the solution. Yes, a tiny amount remains in solution, but we've successfully isolated almost all of it. As we add more carbonate, the iron concentration drops. More precipitation occurs, but there is so little present now that the amount still reacting is negligible compared to what came out before the equivalence point. At a p carbonate of 2, for instance, the iron concentration is down to 2.1 times 10 to the minus 9 molar. Now, 99.9999979% has been removed. But that's only about 5 times 10 to the minus 5% more than we'd already had removed. So let's now return to the consideration of what happens when two precipitable ions are present together in the same solution. Imagine a solution that contains both nickel 2 plus and iron 2 plus ions, both at a concentration of 0.1 molar. These two ions are often found together in nature. How might we quantify the amount of both species that is present? How might we separate the one from the other? If we look up the carbonate ion, we see that it forms a sparingly soluble species with both of these ions. The KSP for iron 2 plus is still 2.1 × 10 to the minus 11, while that for nickel 2 plus is 1.3 times 10 to the minus 7. Here again is a graph of the P function of the carbonate concentration. From the KSP values and with the initial concentrations as given, we see that the iron starts to precipitate at this level, which is the same as before because the initial concentration is the same. While the nickel with the same initial concentration will begin to precipitate at this concentration of carbonate. Here is that same graph of the iron precipitation. And if we can stop adding carbonate at a P carbonate value of 6, the nickel will not have yet started to come out of solution, but the remaining iron concentration will be 2.1 times 10 to the minus 5 molar. We will have already removed 99.979% of the iron from solution. We could filter it off and thereby have separated the iron from the nickel. A separation process that is more than 99.9% effective is actually a very good process. We can use precipitation to separate ions in solution from each other. The concentration at which an ion begins to precipitate depends both on its KSP and also on its own initial concentration. When considering the effectiveness of a precipitation separation, we have to take both properties into consideration. So here's how to deal with this kind of a problem. Consider a solution that contains calcium 2 plus at a concentration of 0.01 molar and barium 2 plus at a concentration of 0.05 molar. We'll add sodium fluoride to precipitate the ions as their fluorides. Which ion will precipitate first, and how much will remain in solution when the second ion begins to precipitate? First, we look up their KSP values. Note that the stoichiometry of the species is no longer 1:1, and that's reflected in the KSP expressions. The fluoride ion concentration is squared. So which precipitates first? Well, even though the stoichiometry of the two systems is the same, we cannot just compare the KSP values because the ion concentrations are not the same. We're actually determining the concentration of fluoride that will start to induce precipitation for each ion. Because the initial concentrations are different, a simple comparison of KSP is not adequate. Now in this case, the KSPs are very different, and the initial concentrations are not too different, so a KSP comparison is likely to be correct, but we should be careful and always do the calculation. For the 0.01 molar calcium ion, a fluoride concentration of 5.7 times 10 to the minus 5 molar will just start to induce precipitation. Note that with this 2:1 fluoride to calcium stoichiometry, we have had to divide by calcium and then take the square root. As always, we have to mathematically solve according to the form of the equilibrium expression. For the 0.05 molar barium ion, a fluoride concentration of 5.5 times 10 to the minus 3 molar will induce precipitation. Which ion will begin to precipitate with a smaller fluoride concentration? It is the calcium. When the barium is just starting to precipitate, the calcium ion concentration has gone down to 1.1 times 10 to the minus 6 molar. It is much smaller than at the beginning, but it's not zero either. What is the portion of the original amount that is present in the solution as a solid precipitate? Well, we have removed 99.989% of the calcium. If we're able to separate the solid from the liquid, then we will have done a pretty good job of separating the two ions. Now here's another example. You be extra careful when the two precipitating species do not have the same stoichiometry. This can be a little tricky. Consider an original solution that contains cadmium and indium ions, both at a concentration of 0.01 molar. We will precipitate them out as their insoluble sulfide species. Which precipitates first? How much of it remains when the second begins to precipitate? Well, look up the KSP values. Note that cadmium is a 2 plus ion, indium is a 3 plus ion, and sulfide is a 2 minus ion. So both KSP values are very small, but the indium sulfide is very, very small at 10 to the minus 70. In determining which precipitates first, you may be tempted to declare the indium sulfide as being most insoluble because its KSP is so much smaller. But the different stoichiometries confuse the issue. What we really want to know is which species begins to precipitate at a smaller sulfide concentration. Now, given these initial metal ion concentrations, which sulfide concentration will initiate precipitation? Note carefully how the different stoichiometry imposes a different mathematical form for each of the equilibrium expressions. Solve each for the sulfide concentration that will just satisfy the equilibrium given the initial metal ion concentrations. The math is different for each one. We have to take a cube root in the indium case. But look at that. The cadmium actually begins to precipitate first. When the stoichiometry is different, you need to calculate both concentrations before making a decision about which precipitates first. How much cadmium is left when the indium starts to come out of solution? Divide by the sulfide concentration when the indium just begins to leave solution. There's 8.75 times 10 to the minus 6 moles left. That means we've removed 99.91% of the cadmium. Again, a very good separation technique.